Hello everyone, welcome back to my YouTube channel. Today I'm going to talk about constructing a binary search tree from traversals. In this presentation, we will learn what trees are, what binary trees are, what traversal means, and most importantly, how preorder and inorder traversals help us reconstruct a binary search tree step by step. I will explain everything in simple, professional and easy to understand way with examples and visual explanations. By the end of this presentation, you will clearly understand how traversal sequence can rebuild an entire BST. So let's begin. Alright everyone, now let's begin the presentation. Our topic is constructing a binary search tree from traversals. Before we learn how reconstruction works, it's important to first understand the basic concept behind trees and binary search trees. So let's start from the foundation of this topic. What exactly is a tree in a computer science? When we hear the word tree, we normally think about nature. But in a computer science, a tree is a structure used to organize data in a hierarchical way. A tree is made up of nodes connected by edges. At the very top, we have the root node. Below that, we have parent and child nodes connected together. And the nodes without children are called leaf nodes. Unlike arrays or linked lists, trees allow data to branch out into multiple paths, making searching and organizing much more efficient. That's why trees are widely used in a system like databases, file management system and search engines. So let's understanding trees first step toward understanding binary search tree and traversal reconstructions. Now let's move to binary trees. A binary tree is a special type of tree where each node can have maximum of two children. These are called the left child and the right child. Binary trees are one of the most important structures in data structures and algorithms. Here are some key characteristics. Each node stores data. Nodes are connected hierarchically, and every node can have up to two children. Binary trees form the foundation of advanced structure like binary search trees, AVL trees, and heaps. So, before understanding BSTs, we must first understand binary trees. Now let's discuss the binary search tree, also known as BST. A BST is a special type of binary tree that follow a strict ordering rule. The rule is all value in a left subtree must be smaller than the parent node, and all value in the right subtree must be greater than the parent node. This rule apply recursively throughout the tree. Because of this structure, BST provide very efficient searching. In an average case, searching, insertion and deletion can be performed in all log n time complexity. That is why BST are useful for fast processing. Let's clearly understand the rules of a BST. Rule number 1. Left child value must always be smaller than parent. Rule number 2. Right child value must always be greater than the parent. Rule number 3. Duplicate values are generally not allowed. And rule number 4 is these same rules apply recursively to every subtree. These rules ensure that the tree remains organized and searchable. Now, let's look at some advantages of binary search trees. First advantage is efficient searching. Because the tree is ordered, we can eliminate half the search space at every step. The second advantage is fast insertion and deletion. The third advantage is automatic sorting. And in order, traversal of a BST always produce sorted output. Another advantage is support for range queries. This makes BST useful in databases and indexing systems. Overall, BST are powerful because they are combined flexible with efficiency. Now we come to a very important topic, tree traversals. Traversals means visiting every node in a tree in a specific order. Traversals are used to process tree data, search nodes, store trees, and reconstruct trees. Without traversals, it would be difficult to understand or rebuild tree structures. There are mainly three types of traversals: preorder, inorder, and postorder. Each traversal follow a unique visiting order. Tree traversal types. First is pre-order traversal. In pre-order, we visit root, left, right. This means we process the root first. Second is in-order traversals. In order, we visit left, root, right. For BSTs, in-order traversal always give sorted output. Third is post order traversals. In post order, we visit left, right, root. For BST reconstructions, pre order and in order traversals are especially important. Now we come to the main concept of today's presentation. How do traversals help reconstruct a BST? The answer is simple. The first element in a pre-order traversals is always the root node. Then we locate that root inside in-order traversal. Everything on the left side belongs to the left subtree. Everything on right side belongs to right subtree. Then we recursively repeat the same process for subtrees. So the key idea is preorder tell us which node is the root. Inorder tell us where the split the tree. Together they uniquely define the BST structure. Now let's see the step by step algorithm. Step 1. Take the first element from preorder traversal. That becomes the root. Step 2. Find the root in inorder traversal. Step 3. Split the inorder traversal into left and right parts. Step 4. Recursively repeat the process for left and right subtrees. Step 5. Continue until all nodes are placed correctly. This recursive process builds the full binary search tree. Let's use an example. Pre-order traversal is 8, 5, 1, 7, 10, and 12. In-order traversal is 1, 5, 7, 8, 10, 12. Notice that the first element is in pre-order is 8. So immediately we know that 8 is the root node. Now we will use in-order traversal to divide the tree. Let's identify the root. First, pre-order element is 8. So 8 becomes the root of the BST. Now find 8 in in-order traversals. Element before 8, 1, 5, 7 belongs to the left subtree. Elements are 8, 10, 12 belong to the right subtree. Now the tree has been divided into two parts. Now we construct the left subtree. The next preorder element is 5. So 5 becomes the left child of 8. In order sequence, 1 is on the left of 5 and 7 is on the right of 5. Therefore, 1 becomes the left child of 5 and 7 becomes the right child of 5. Now the left subtree is complete. Now we construct the right subtree. The next preorder value is 10. So 10 becomes the right child of 8. In order traversal, 12 is on the right side of 10. So 12 becomes the right child of 10. Now both subtrees are complete and the BST structure is fully reconstructed. Here we can see the final BST. The root is 8. The left subtree contains 5 with children 1 and 7. The right subtree contains 10 with child 12. Now we verify the tree. If we perform pre-order traversals, we can get 8, 5, 1, 7, 10 and 12. If we perform in-order traversal, we can get 1, 5, 7, 8, 10 and 12. Both sequences are matched perfectly. So the reconstruction is correct. Now I will demonstrate how to insert values into binary search tree step by step. First I insert 8 and it becomes the root node. Next I insert 3. Since 3 is smaller than 8, it goes to the left side. Next I insert 10. Since 10 is greater than 8, it goes to the right side. Next, I insert 1. It goes to the left side of 3 because it is smaller than 3. Then I insert 6. It goes to the right of 3 because it is greater than 3. Next, I insert 14. It goes to the right of 10. Then I insert 4, which goes to the left of 6. Next, I insert 7, which goes to the right of 6. Finally, I insert 13, which goes to the left of 14. After all insertion, the binary search tree is successfully formed. Let's summarize the algorithm quickly. Use preorder to identify roots. Use inorder to divide left and right subtrees. Apply recursion repeatedly. Continue until all nodes are placed. This method successfully reconstructs the BST. BST are widely used in real-world systems. Some applications include database indexing, file organization, expression parsing, and network routing. BST helps system perform searching and sorting efficiently. That is why they are important in computer science. BST have many advantages. They provide fast searching, fast insertion, and sorted data retrieval. However, BST also have limitations. If the tree becomes unbalanced, performance can be degraded to ON. To solve this problem, self-balancing trees like avial trees and red black trees are used. To conclude, we learned what trees are, what binary search trees are, what traversal means, and how preorder and inorder traversal reconstruct a BST. Pre-order traversal helps identify the route, while in-order traversal divide the tree into left and right subtrees. By recursively applying these concepts, we can rebuild the complete binary search tree. This concept is very important in data structure and algorithms. Thank you everyone for listening to my presentation. I am truly appreciate your time and attention. I hope this presentation helped you to understand how to construct a binary search tree from traversals in simple and clear way. If you enjoy this presentation and learning something new, don't forget to support my channel by liking, sharing and subscribing. And yes, we will see you in my next video. Thank you once again. Bye bye.